So we are on this problem, number of 1 bits. We are given a positive integer n. Write a function that returns the number of set bit in the binary representation of that number. And this is also called as a Hamming weight. Let's say we have n equals to 11. What would be the binary representation of it? 1, 0, 1 and 1. The number of 1 we can see over here is 3. How do we calculate it? There is a very simple method which we can use. We can multiply this number with 1, and that would give us a 1 in this case. If it gives a 1, we can say that the last bit over here is 1. So we made one calculation. So, okay, the number of 1 right now is 1. After that, we shift this number to the right, which means this number becomes 101. And then we multiply this with 1. Over here, this gives us a 1 again. So we can say that the count, again, we added 1 more. So the count overall is 2. We can shift this number again. That would be 1, 0. Multiply that with 1 and 1. Over here, this gives a 1. The number of ones is 0 over here. The 2 does not change. Shift this number again. I have a 1 and 1. I get a 1. So this count is again 1. This 2 can be incremented. So I have 3 number of ones. This is a very simple and a very naive approach. Can we solve it better for larger results? Because if we have something like this, we need to make a shift 32 times. Can we solve it better? So to solve this problem better, let's make an observation. Let's say I have a number like 10100. How about I subtract 1 from it? What would happen? This 1 would become a 0. This would become a 1 and this would become a 10. I subtract, so this would be 2 minus 1 and I would get a 1 over here. This would be 1, this would be 0, this would be 0, this would be 1. So the observation is, in any binary number, when we subtract a 1, the one from the right, the first one from the right becomes 0 and every other number is incremented, and in the output we get something like this. This value became a 0 and these are all 1, and this would always happen with any other number, which means we destroyed this 1 over here. How about we multiply these numbers, which would give us 10000. This would be the output. So what did we actually do? We were actually hunting for the first one, and we just destroyed this first one, and now we are left with just one more one. We can apply this to any number. How about 101 and 1? Reduce 1 from it. We get what? We get 1010. Multiply these two numbers. We get a 1010. We destroyed this one. We are left with two ones. How about we destroy them even further? Let's subtract 1 again. What do we get? We get 10. This becomes a 0 and we get a 1 over here. Let's multiply these two. What do we get? 100 and 0. We destroyed another one. How about we do it again? Subtract 1 again. We get a 0, 1, 1 and 1. Multiply these two. What do we get? 0, 0, 0, 0. We have all the ones are destroyed. So how many iterations it took? 1, 2 and this one 3. It took us 3 iterations to destroy all the ones. And this is the algorithm. The time complexity would be the number of ones present in your binary number. Let's see how do we implement it in code. So I am here in the code editor. I am given this function hamming weight and the number n is the input. Let's say I have a result assigned to 0 initially. I have 0 number of 1 bits at this point. Next, every time we destroy a part of that number and we do it until we reach 0. We can say while n is greater than 0, let's continue. If it becomes 0, we end this loop. After that, what we need to do is we need to take n and we need to multiply that with n minus 1. This is what we were doing, calculating n minus 1, multiplying that with n. And we would change the value of n itself, which means I would assign it. This would be the new value of n and eventually it will become 0. The number of iterations it would take would be the uh, solution of this problem. So over here I can say result plus 1 plus 1. In the end, when we have n 0 and we end this loop, we can return this result. Let's submit this code. We have it passing.